Hey guys, it is officially 1:42 a.m. and we are doing organic chemistry, so let me get a woohoo! No, I'm just joking. It's going to be a great video. I hope it helps you all out. Okay, so for aromatic compounds, where should we begin? We should begin with some common names of some common aromatic compounds. So, the aromatic compounds you're most likely to come across in your organic chemistry class are going to consist of chlorobenzene, toluene, benzene, orthoxylene, nitrobenzene, phenol, methoxybenzene/anisole. Those are the same molecule, just different names. Aniline, benzoic acid, benzaldehyde, styrene, and acetophenone. I probably just butchered that name. I said like ass, but I'm sorry. Okay, now then the acronyms you want to remember for these. Chewbacca treats babies only, never Padme, Maul, Anakin, Boba, because Star Wars amazes. And if you can remember that acronym and fill in these words, all you have to remember is the substituents themselves, which I am about to show you right now. So chlorobenzene is just a chlorine attached. If that was bromobenzene, it would be a bromine attached. If that was iodobenzene, it would be an iodine attached. If that was fluorobenzene, it would be a fluorine attached. But since it's chlorobenzene, we will put our chlorine halogen back in there. Toluene is just a single methyl attached to the benzene ring. Benzene, don't even touch it. It's the exact same thing that I have drawn there. Orthoxylene is two methyl groups side by side, or ortho in configuration. Nitrobenzene is a benzene ring with your nitro group attached on, and the nitro group is a positively charged nitrogen with a double bonded oxygen and a single bond oxygen that carries a negative charge. Phenol is just OH attached to the benzene ring. Aniline is NH2. Methoxybenzene or anisole is an oxygen. My bad, didn't mean to draw that. Sorry. An oxygen, my God, attached to a methyl, or CH3. Benzoic acid is a benzene ring with a carboxylic acid attached to it. And then benzaldehyde looks very similar, however, instead of that OH, it's got a hydrogen on there. Styrene is a benzene ring with this bad boy on it. Acetophen, once again said ass, I apologize, is basically a carboxylic acid, but instead of the OH, it's got a methyl on it. And here we go. On to the next thing. So, configurations. You got ortho, meta, and para. So, ortho, the substituents are right next to each other. Meta, the substituents have one carbon in between. And para, the substituents have two carbons in between. So, if I draw this out, ortho, side by side, no carbons in between. X is what I'm going to use to represent substituents, because it could be any of those substituents I just listed back there. Meta, one carbon in between. And para, basically opposite points or two carbons in between, if you want to think of it that way. Those are your configurations to remember. So let's do some examples with these configurations. Now you guys can pause the video and work these out, but I'm going to answer them right now. So ortho, meta, para, remember. Ortho, side by side, so we would have a chlorine next to a nitro group. Para, we would have opposite ends, methoxy, and then we would have toluene, which is just a methyl. Meta-chlorobenzaldehyde. One carbon in between. Cl, benzaldehyde. Just like that. I hope you guys understand that. It's not too hard. Just you don't have to be able to number it and name it. He's gonna give you the name, and the ACS is gonna give you the name. All you have to be able to do is translate it onto paper. So you're gonna be given orthochloronitrobenzene, and you're just gonna have to be able to translate it by knowing that para, ortho, and meta are different configurations, and then of course these different common name substituent groups. So now let's actually look at what makes something aromatic. So the first role, no sp3 hybridization. I'll show you these roles in depth. I'm just going to name them off first. No sp3 hybridization. Second role, continuous pi orbitals. Third role, it has to be a cyclic compound. that's the easiest rule to remember. Basically, it has to be in a ring. And then Huckel's rule. And Huckel's rule, right out real quick. That goes 2, 6, 10, 14, then just keep adding 4 on there. I mean, you could go to 1,000,000 if you really wanted to. Actually, I don't know if you keep adding 4, if you get to 1,000,000, it might be some different number, but you know what I'm saying. So let's take a look at what no sp3 hybridization means. So for this molecule right here, is it aromatic? It is not aromatic because there are actually hydrogens on here. And these carbons right here and here are actually sp3 hybridized and sp3 hybridized. And that means that no resonance can occur here. So, since that's the case, since resonance can occur here, that means there's no continuous pi orbitals. And what a continuous pi orbital is it's basically continuous resonance in a circle. And that's why benzene's such a great compound to go back to actually teach this concept. Because benzene has Huckel's rule, it has continuous pi orbitals, and there's no sp3 hybridized atoms on here. So, let's move on to Huckel's rule in depth. So, Huckel's rule explored. Each pi bond or lone pair contributes 2 pi electrons to the cyclic compound. So what that means is, for example, I got my benzene here, because like I said, I like to always go back to benzene. Start with the basics and then work your way up. We have 1 pi bond, 2 pi bonds, 3 pi bonds. So that would be 2, 4, 6. That means there is 6 pi electrons in the system, and that follows Huckel's rule, which is once again 2, 6, 10, and then 14. You just keep adding 4 onto it. So since this is 6 electrons, it follows Huckel's rule. It has continuous pi orbitals. It is a cyclic ring, and there's no sp3, so this is 100% aromatic. And like I said back here, these are the rules you have to follow. And now I'm just going in depth with these rules. But since this is aromatic, it's aromatic. So let's keep exploring Huckel's rule. Some molecules look like they have more pi electrons than they actually do, but due to orbitals, only one participates in Huckel's rule. So what I mean by that is, if you look at this molecule right here, you see a lone pair and you see a double bond attached to the nitrogen. Only one of these participates in Huckel's rule. So that means only one of these will contribute 2 pi electrons. They both won't. Only one will contribute the 2 pi electrons. So we have 2 there. Then of course, we have 2 here. And I forgot to put the pi symbol there, but you guys catch the drift. And we have 2 here. So that'd be 2, 4, 6. It is a continuous pi. It is continuous conjugation, meaning it can continuously flow. It is a cyclic ring, so this is 100% aromatic. So, same thing occurs with this molecule right here. You would want to say that you'd want to count both of these, but that is not the case. You only count one because they are in. The one doesn't contribute because it's in an orbital that can't contribute to the cyclic ring, so it doesn't count. So, this would be 2, 4, 6, 100% aromatic. Same thing with this. It looks like it wouldn't be aromatic because of this weird negative charge up here, but only this contributes to the aromaticity of this compound. So it would be 2, 4, 6. This would be 100% aromatic. And we're going to do some examples at the end, and we'll go even more in depth, and I'll throw everything at you at once, but I don't want to overwhelm you. It's not good just to overwhelm somebody with all these rules all at once, so we're going to go in depth with each rule. So triple bonds in Huckel's rule. Triple bonds only contribute 2 pi electrons to the overall Huckel's rule. And once again, that's because one of these bonds is not in the proper orbital to actually contribute to the aromaticity of the compound. So it doesn't count. We just have to count it as 2 electrons. So for example, you don't count both of these, you only count one. So it is 2, 4, 6. This is aromatic, but I do want you to know this is an intermediate and it is highly unstable. But it is aromatic. Moving on. So now we got some examples to solve on our own. So this first one, is this aromatic? 2, 4, it already failed Huckel's rule, plus it's sp3 hybridized on both ends. So it is not aromatic. Next one, 2, 4, we have an open orbital right here to move into, but once again only 4 pi electrons, so doesn't follow Huckel's rule. It's not aromatic. So for this one, let's see. We have, once again, you only count the double bond, or you could count the lone pair if you wanted, but you only count one. Only one contributes to the compound. So 2, same thing for this one. 4, 6. This is aromatic. There's no sp3 hybridized atoms in here. It is cyclic. It has continuous pi orbitals, so continuous resonance basically in a circle. And then once again, only the lone pair or the bond attached to the nitrogen participates in the resonance around the ring, not both. So for this molecule, is it cyclic? Yes. It has a positive charge on it, meaning you could resonate up here and you could boom, boom, move that then here, but that means it has a continuous orbital. It has 2 pi electrons, so it follows Huckel's rule. No sp3 hybridized atom in here, so by gosh, it is aromatic. Okay, so the next one, is this aromatic? Well, follows Huckel's rule, has 2 pi electrons. However, we got these bad boys up here, and that makes this carbon right here sp3 hybridized, so no. God, my handwriting looks like a toddler's right there. Okay, so next molecule. We have, let me see, 2, 4, 6, and it has continuous pi orbitals open to resonate around in a circle. So it is 100% aromatic. Moving on. Got a couple more here for you guys. So looking at this molecule, is this aromatic? 2, 4. You could either count the lone pair or the pi bond. I'm going to count the pi bond. And that'd be 2, 4, 6. It has continuous resonance in a circle, meaning continuous pi orbitals are open. No sp3 hybridized atoms, so it's 100% aromatic. Next molecule, let's count these up. 2, once again, only one of these counts towards the aromaticity of the compound if you are trying to determine aromaticity. 4, 6, 8. 8 pi electrons, that does not follow Huckel's rule. It is cyclic, however, but it doesn't follow Huckel's rule, so this is not aromatic. Gosh. Okay, so we got a cyclic ring, but I have jack shit in it, so that's not aromatic. Okay, so I don't even have a cyclic ring with this one, so I hope you don't think this is aromatic, because it is not. It does have 2, 4, 6 pi electrons, but once again, it's not a cyclic ring, and that is a rule that it has to follow, so not aromatic. If you missed that on an exam, I would feel very sorry for you. Okay, so moving on to the final product. We have 2, because remember, only this lone pair or the pi bond can contribute. You can pick whatever one you want to count 2 electrons towards Huckel's rule. 2, 4, 6. It's in a cyclic ring. It has continuous resonance or continuous pi orbitals open, meaning it is shit. No, it's not shit. It's aromatic. I didn't mean to use the highlighter. So, I hope this all helped. If you guys have any questions, it's basically just following Huckel's rule and understanding how some of these atoms only contribute one or the other. They don't contribute both due to pi orbitals. So, I will leave you guys with that. I hope you guys have a wonderful night and stay frosty.